Look up at the night sky, really look at it, and tell me what you see. Stars, galaxies, the vast expanse of space stretching beyond our comprehension. But here's the unsettling truth. What we're seeing is only a fraction of reality. In fact, everything you've ever known, every planet, every star, every speck of light in the cosmos, makes up just 5% of the universe. The rest, it's missing, or at least it's hiding in plain sight. Scientists call this the greatest mystery in modern physics, the case of the universe's missing energy. Where did it go, what form does it take, and why does the universe seem to be playing an elaborate game of cosmic hide and seek with us? This isn't just a small gap in our understanding, it's a yawning chasm. Imagine pouring a glass of water and watching 95% of it vanish before your eyes. That's essentially what's happening with the universe. The math doesn't add up. The energy we can observe, the light, the matter, the gravity we can measure is just a drop in an ocean we can't see. The rest is locked away in two shadowy enigmas, dark matter and dark energy. Dark matter, an invisible scaffolding that holds galaxies together, and dark energy, a mysterious force ripping the universe apart at the seams. They don't emit light, they don't interact with matter as we know it, and yet, they dictate the fate of everything. So why should you care? Because this isn't just a puzzle for scientists in lab coats, it's a question that strikes at the heart of existence itself. If we're wrong about what makes up the universe, what else are we wrong about? The rules of physics, the nature of reality, even the ultimate destiny of the cosmos could be rewritten, and that's what makes this search so thrilling. We're on the brink of discoveries that could redefine our place in the universe, and you're here to witness it. Over the next few minutes, we'll dive into the most compelling theories about this missing energy, some bold, some bizarre, all mind-bending. So buckle up, the universe has secrets and we're about to uncover them. Let's start with the most mind-bending idea of all. Empty space isn't empty, not even close. According to quantum mechanics, what we call a vacuum is actually a seething, bubbling sea of energy. Tiny particles pop in and out of existence so fast, they're gone before we can even detect them. This isn't science fiction, it's a real phenomenon called quantum fluctuation, and it might hold the key to the universe's missing energy. Think of it like this: imagine a calm lake at night. On the surface it looks perfectly still, but if you could zoom in, you'd see countless tiny ripples, waves crashing into each other at the smallest scales. That's what's happening in the so-called emptiness of space. These fluctuations aren't just random noise, they carry real energy, and when physicists calculate how much energy should be there, the numbers are staggering. So much, in fact, that if we could tap into it, we'd have more power than all the stars in the universe combined. This is where Einstein's cosmological constant comes in. Back in the early 20th century, he proposed that empty space itself could have an intrinsic energy, a kind of anti-gravity pushing the universe apart. At the time, he abandoned the idea, calling it a greatest blunder, but now, turns out he might have been onto something. Modern observations show the universe isn't just expanding, it's accelerating, as if some invisible force is stretching space itself. That force could be the quantum energy of the vacuum, constantly driving the cosmos outward. But here's the catch: when scientists calculate the expected energy from these quantum fluctuations, the number is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in the history of physics. Some call it the vacuum catastrophe, and it's left researchers scratching their heads. If quantum vacuum energy is real, why isn't it tearing the universe apart? Or maybe it is, and we just don't understand the full picture yet. One possibility is that our math is missing something, a hidden symmetry, a cancellation effect we haven't discovered. Another wild idea: there could be multiple universes, each with its own vacuum energy, and we just happen to live in one where the numbers line up in a way that allows galaxies and life to exist. Whatever the answer, one thing's clear: the quantum vacuum isn't just background noise. It could be the invisible engine driving the fate of everything. But what if the answer isn't an invisible substance at all? What if, instead of chasing shadows, we've been misunderstanding gravity itself? That's the radical idea behind modified Newtonian dynamics, or MOND for short. Forget dark matter. This theory suggests that gravity doesn't play by the same rules everywhere. On the scale of galaxies, it might bend the laws we thought were set in stone. Think about a carousel spinning so fast that the usual rules of motion seem to break down. Kids clinging to the edges would feel a force stronger than expected, as if something unseen were pulling them outward. That's how galaxies behave. Stars at their outer edges orbit much faster than Newton's laws predict, as if an invisible hand is tugging at them. Dark matter was invented to explain that extra pull, but MOND asks, what if gravity just works differently out there? Instead of inventing new particles, maybe we need to tweak the equation itself. Here's where it gets interesting. In the 1980s, physicist Mordechai Milgrom proposed that when gravity's grip becomes extremely weak, like at the fringes of galaxies, it doesn't fade as quickly as Newton or Einstein predicted. It lingers just enough to explain those runaway stars without calling on dark matter, and in some cases MOND nails it. Certain small galaxies rotate exactly as this modified gravity predicts, no dark matter required. It's as if we've been trying to solve a puzzle with the wrong pieces, and MOND hands us the right ones, at least for some corners of the cosmos. But before we toss out dark matter entirely, there's a catch. MOND stumbles when faced with the biggest scales of the universe. Galaxy clusters, for instance, still seem to pack way more mass than visible matter can account for, even with tweaked gravity. And then there's the cosmic microwave background, the afterglow of the Big Bang. Its patterns fit snugly into models laced with dark matter, leaving MOND scrambling for explanations. So is MOND a revolutionary fix or a fascinating dead end? The debate rages on. Some physicists see it as a stubborn outlier, a theory that works in a few special cases but fails the universal test. Others argue we might be missing a deeper version of MOND, one that could bridge these gaps. After all, Einstein's relativity once upended Newton's apple cart, proving that even the most trusted laws have their limits. Could gravity on galactic scales be due for another rewrite? One thing's certain: MOND forces us to question assumptions we've taken for granted. It's a reminder that sometimes the boldest answers don't come from adding more pieces to the puzzle, but from realizing the puzzle itself might be different than we thought. Whether it's right or wrong, it's shaking up the hunt for the universe's missing energy, and that's how science moves forward. Now, let's talk about the leading suspects in the case of the universe's missing energy, particles so elusive they've dodged detection for decades. Enter WIMP, or weakly interacting massive particles, the frontrunner in the hunt for dark matter. These hypothetical particles are the ninjas of the cosmos, massive enough to bend space with their gravity, yet so stealthy they barely interact with ordinary matter. If they exist, they could be everywhere around us, streaming through your body right now without a trace. The logic behind WIMP is elegant. In the early universe, physicists believe a storm of particles raged at unimaginable energies. As things cooled, most of these particles decayed or clumped into the atoms we know today, but WIMP, they'd be the survivors, stable, heavy, and just interactive enough to stick around in vast numbers, forming the invisible skeleton of galaxies. It's a compelling story, but there's one problem: we've never caught one. That's where the hunt gets thrilling. Deep underground, far from the interference of cosmic rays, scientists have built ultra-sensitive detectors waiting for a WIMP to bump into an atomic nucleus. Imagine a skyscraper-sized lab buried beneath a mountain, filled with vats of liquid xenon or chambers of ultra-pure germanium. These experiments operate in near absolute darkness, colder than deep space, because even a single stray photon could drown out the faint signal of a WIMP collision. So far, silence, but that hasn't stopped the search. Then there's the brute force approach, particle colliders. If WIMP are hiding in the cracks of physics, smashing protons together at near light speeds might shake them loose. The Large Hadron Collider, the same machine that found the Higgs boson, has been scouring its debris for anomalies missing energy in the aftermath of collisions that could hint at WIMP slipping away undetected. Yet despite decades of effort and billions of dollars, the detectors remain stubbornly quiet. This leaves scientists at a crossroads. Are WIMP just too shy, requiring even more sensitive experiments? Or are we chasing a ghost, a beautiful theory undone by nature's refusal to cooperate? Some researchers are doubling down, designing next-generation detectors with even greater precision. Others are exploring darker horses, lighter particles, hidden dimensions, or even primordial black holes born in the chaos of the Big Bang. The mystery of dark matter is far from solved, but one thing's certain: the longer WIMP evade us, the more we're forced to question what else might be lurking in the cosmic shadows. What if the universe's missing energy isn't hiding in some exotic particle we've yet to imagine, but in something so subtle, so lightweight, it's been dancing right under our noses? Enter axions, the dark horse candidate for dark matter. Unlike their heavyweight cousins the WIMP, axions are feather-light, with a theoretical mass so small it's almost poetic. A single axion might weigh as little as a billionth of an electron, but don't let their size fool you. If they exist, there could be quadrillions passing through you every second, a ghostly rain you'd never feel. The story of axions starts not with dark matter, but with a puzzle in particle physics. In the 1970s, scientists noticed something odd. The strong nuclear force, which glues atomic nuclei together, obeys a near-perfect symmetry called CP invariance. But why nature rarely plays by such strict rules? To explain this, physicists Roberto Pexi and Helen Quinn proposed a new field that would tweak the equations just enough to keep everything balanced. The particles tied to this field, axions, originally they were just a mathematical fix, but then someone realized these tiny particles could solve two cosmic mysteries at once. Here's how it works. In the seething chaos of the early universe, axions would have been born in unimaginable numbers. As space expanded and cooled, they'd stop interacting with normal matter almost entirely, freezing into an invisible ocean. No electric charge, no strong nuclear ties, just a faint whisper of gravity. Multiply that by the sheer volume of the cosmos, and suddenly, you've got enough mass to explain why galaxies spin too fast and why light bends around empty space. But how do you catch something that barely interacts with anything? Scientists are getting creative. One approach turns the entire Milky Way into a trap. Since axions might occasionally convert into photons in the presence of strong magnetic fields, researchers have built devices like the Axion Dark Matter Experiment, a high-tech light switch buried in a Seattle lab. Inside, a supercooled magnet waits for even the faintest flicker of microwave photons that shouldn't be there, a sign that axions are dancing through. Then there's the quantum twist. Some theorists suggest axions could form bizarre, galaxy-spanning waves with peaks and troughs of dense and sparse dark matter. If true, we might spot their fingerprints in the way stars subtly wobble over time. Others are hunting for axions born in the hearts of stars, or even in the explosions of collapsing neutron stars. Every flicker of unexplained light, every anomaly in cosmic magnetic fields, could be a breadcrumb trail leading to them. The stakes couldn't be higher. Axions aren't just a dark matter fix, they could rewrite our understanding of particle physics. If found, they'd prove the existence of an entirely new class of ultra-weak particles, opening doors to realms of physics we've barely dreamed of. And yet they remain elusive. Some experiments have seen tantalizing hints, a blip here, a statistical bump there, but nothing conclusive. The hunt is a high-stakes game of patience, where every negative result narrows the hiding places. So why keep searching? Because axions represent something rare in science, a theory elegant enough to solve two puzzles at once, yet humble enough to hide in plain sight. They remind us that sometimes the universe's biggest secrets aren't held by the loudest forces, but by the quietest whispers, and if we're listening closely enough, we might just hear them. Among the most elusive candidates for dark matter, there's a particle so slippery it makes ordinary neutrinos, already famous for their shyness, look downright social. Meet sterile neutrinos, the hypothetical ghost of the ghost. If they exist, they could solve two puzzles at once: the missing mass of the universe and the strange behavior of their more familiar neutrino cousins. Neutrinos are already cosmic enigmas. Trillions pass through your body every second, leaving no trace. They're born in nuclear reactions, from the sun's core to supernova explosions, barely interacting with anything along the way. But sterile neutrinos take this aloofness to another level. Unlike regular neutrinos, we'd at least grudgingly acknowledge the weak nuclear force. Sterile neutrinos would ignore all forces except gravity. That's why they're called sterile, utterly clean of any interaction with the universe's other building blocks. The idea emerged from a glitch in neutrino experiments. When scientists measure how neutrinos oscillate, changing flavors between electron, muon, and tau types, the numbers don't quite add up. There's a discrepancy, a flicker of missing energy in the data. Some researchers think sterile neutrinos could be the culprit, an extra flavor lurking just beyond our detectors, subtly skewing the results, but the implications go far beyond lab anomalies. If sterile neutrinos are real, they could have been forged in the furnace of the Big Bang, lingering as a vast, invisible sea. Their gravity would sculpt galaxies just like dark matter does, yet they'd leave no other fingerprints. There's even a tantalizing clue from space. Certain X-ray emissions from distant galaxies and clusters don't have a clear explanation. One theory: sterile neutrinos decaying ever so slowly, releasing a faint glow we're only now learning to see. The hunt is on. Deep underground labs like Fermilab are tweaking neutrino beams, searching for wobbles that hint at a fourth, sterile type. In space, telescopes scour X-ray maps for that elusive decay signal. It's a long shot, but if found, sterile neutrinos would crack open particle physics and cosmology at once. We'd finally have a dark matter candidate that's not just hypothetical, but one with roots in the known neutrino family. Yet the mystery deepens. Some models suggest sterile neutrinos could be extraordinarily light, barely weighing more than a thought. Others propose they're surprisingly heavy, clumping together in ways that reshape galaxy formation. And then there's the wildest idea, that they're not particles at all, but ripples in extra dimensions we can't perceive. What makes sterile neutrinos so compelling is their duality. They're grounded enough to fit within existing physics, yet strange enough to rewrite the rules. Whether they're the answer or another dead end, they remind us that the universe's secrets often lie not in the glaring voids, but in the quietest gaps between what we see and what we expect. What if the universe's missing energy isn't in particles at all, but in black holes so old, they've been hiding since the dawn of time? This is the audacious idea behind primordial black holes, hypothetical relics of the Big Bang that could be lurking unseen in the cosmic shadows. Unlike the black holes we know born from collapsing stars, these would have formed in the first chaotic moments of the universe, when space itself was a seething, dense soup. Imagine a newborn cosmos so turbulent that pockets of matter crumpled under their own weight, pinching off into tiny, dark knots before stars even had a chance to ignite. The math is tantalizing. If enough of these primordial black holes exist, their combined gravity could explain dark matter's grip on galaxies. They'd be invisible, drifting between stars like ghosts, their presence felt only by the way they bend light and tug on the fabric of space. Some could be as light as an asteroid, others as massive as 1,000 suns, and here's the kicker: unlike WIMP or axions, we wouldn't need new physics to explain them. They be built from the same gravity Einstein described just hiding in plain sight, but how do you hunt for something that emits no light? Microlensing offers a clever clue. When a black hole passes in front of a distant star, its gravity acts like a lens, bending the star's light and causing a temporary brightening. Astronomers have scoured the skies for these telltale flashes, hoping to spot an army of primordial black holes. The results mostly silence. Surveys like OGLE and HSC have ruled out vast swaths of possible masses, meaning, if these black holes exist, they can't be too common in certain size ranges. Yet the door isn't completely closed. Some gaps remain, particularly for black holes lighter than the Moon or heavier than a star. There's even a wild card. What if they're not black holes as we know them, but strange quantum objects called Planck stars, remnants of a universe before the Big Bang? Or maybe they've since evaporated, thanks to Hawking radiation, leaving behind only faint echoes. The beauty of this theory lies in its simplicity. No new particles, no exotic forces, just gravity doing what it does best. But the lack of evidence is a growing puzzle. If primordial black holes are out there, they're masters of disguise, leaving just enough wiggle room in the data to keep scientists guessing. And that's what makes them so fascinating. In a cosmos full of shadows, they remind us that sometimes the darkest secrets are the ones written in gravity itself. What if dark matter and dark energy aren't separate entities at all but two faces of the same cosmic enigma? That's the daring premise behind the dark fluid theory, a radical idea that unifies the universe's greatest mysteries into one elegant, if perplexing, substance. Picture a single exotic fluid flowing through the cosmos, sometimes acting like an invisible scaffold holding galaxies together, other times stretching space itself apart. It's a mathematical masterpiece, stitching together two puzzles with a single thread, but like all grand theories, it comes with its own set of riddles. The math behind dark fluid is undeniably beautiful. Instead of juggling separate equations for dark matter's gravity and dark energy's repulsion, physicists can describe both with a unified framework. Think of it like water, calm and cohesive in a glass, yet capable of carving canyons when set in motion. Dark fluid would shift its behavior based on its surroundings. In dense regions like galaxy clusters, it could clump like dark matter, exerting gravitational pull. In the vast voids between galaxies, it might thin out and accelerate expansion, mimicking dark energy. One substance, two roles, a cosmic chameleon, but elegance alone doesn't make a theory true. The real challenge lies in testing it. Unlike WIMP or axions, dark fluid wouldn't leave behind the same fingerprints. Traditional dark matter searches rely on spotting particles colliding in detectors, but a fluid wouldn't behave that way. Instead, scientists would need to look for subtle anomalies in the way galaxies move, or how light bends around empty space, clues that gravity itself might be playing by different rules in different places. There's another twist. Dark fluid would challenge our understanding of time. Most models treat dark energy as a constant force, but if it's part of a dynamic fluid, its strength could change over cosmic epochs. Early in the universe, it might have behaved more like dark matter, helping galaxies form. Today, it could dominate as dark energy, driving accelerated expansion. Tomorrow, it might shift again, rewriting the universe's fate. Critics argue the theory is too flexible, a just-so story that can explain anything but predict nothing. Yet its defenders counter that flexibility might be its strength. After all, nature rarely adheres to human simplicity. If dark fluid exists, it would remind us that the universe's greatest secrets might not fit into neat categories. They could be fluid, evolving, and far stranger than we've dared to imagine. So where does that leave us? In some ways, dark fluid is the ultimate cosmic wildcard, a theory bold enough to unify the unknown but still slippery enough to evade proof. Whether it's a groundbreaking insight or a dead end, it forces us to think bigger, to question whether the missing pieces of the universe are separate at all. And that in itself is a revelation. Picture a substance so strange, it defies the usual categories of matter and energy, a cosmic shapeshifter that starts out behaving like dark matter, only to transform into something resembling dark energy over time. This is the essence of Chaplygin gas, one of the most intriguing dark fluid candidates out there. Named after a Russian physicist from the early 20th century, this hypothetical substance offers a bold solution to the universe's missing energy problem. What if we're not dealing with two separate mysteries, but one phenomenon that evolves? At its core, Chaplygin gas is a mathematical marvel. In its early stages, it acts like a pressureless fluid clumping under gravity just as dark matter does, providing the invisible scaffolding that holds galaxies together. But as the universe expands and this gas thins out, its pressure begins to dominate. Suddenly, it stops pulling and starts pushing, accelerating cosmic expansion in a way that mirrors dark energy. It's as if the universe's missing energy has been hiding in plain sight all along, shifting its role based on the conditions around it. To grasp how this works, think of a cosmic chameleon. Imagine a puddle of liquid that starts out thick and syrupy, clinging to itself and forming structures, much like dark matter's gravitational grip on galaxies. But as time passes and the universe grows colder, more sparse, that same puddle evaporates into a mist, spreading outward with relentless pressure. That's Chaplygin gas in action, one substance, two phases, seamlessly transitioning to meet the needs of a changing cosmos. The beauty of this theory lies in its economy. Instead of inventing separate entities for dark matter and dark energy, it rolls them into a single package. Some models even suggest Chaplygin gas could emerge naturally from higher dimensional physics or string theory, offering a bridge between the quantum world and the large-scale structure of the universe. But as elegant as it sounds, there's a catch. Real-world evidence is thin on the ground. Observations of galaxy rotation curves and cosmic microwave background patterns don't quite match the predictions of pure Chaplygin gas models, at least not without some tweaks. Some physicists propose hybrid versions, where Chaplygin gas shares the stage with a dash of traditional dark matter. Others suggest it might interact weakly with ordinary matter, leaving faint traces in the way galaxies cluster over time. What makes Chaplygin gas fascinating isn't just its potential to solve two puzzles at once, it's the way it challenges us to rethink the nature of cosmic ingredients. Maybe the universe's missing energy isn't a collection of unrelated oddities, but a dynamic substance with phases we're only beginning to understand. Whether it's the ultimate answer or just another step toward the truth, Chaplygin gas reminds us that sometimes the most profound secrets are hidden not in complexity, but in simplicity waiting to be uncovered. Here's a wild thought: what if our three-dimensional universe, with all its galaxies, stars, and planets, is nothing more than a hologram, a cosmic projection, an illusion painted onto a two-dimensional surface at the edge of reality? It sounds like science fiction, but the holographic principle is a serious theory with roots in black hole physics, and it might just hold the key to the universe's missing energy. The idea starts with a paradox. When matter falls into a black hole, it vanishes from our observable universe, but according to quantum mechanics, information can never truly be destroyed. So where does it go? In the 1970s, physicist Jacob Bekenstein discovered that black holes encode information about everything they swallow on their event horizons, the invisible boundaries from which nothing escapes. Think of it like a cosmic scratchpad. Every atom, every particle that falls in gets scribbled onto the black hole's surface in tiny, plank-sized pixels. Later, Stephen Hawking showed these pixels aren't static, they glow with what we now call Hawking radiation, slowly leaking information back into the universe. This led to a stunning realization: the maximum amount of information a region of space can hold isn't determined by its volume, but by its surface area. It's as if the universe is a giant hard drive, and all the data every star, every planet, every grain of dust is stored in its outer shell, the three-dimensional world we experience. Just a projection, like a movie playing on the walls of a vast cosmic theater. So how does this connect to dark energy? If the holographic principle is true, it would fundamentally change how we calculate the universe's energy budget. Normally, physicists sum up all the energy in three-dimensional space, but if reality is encoded on a 2D surface, those calculations might be missing a critical piece. Some theorists suggest this could explain why the vacuum energy we observe is so much smaller than predicted. The mismatch might not be an error in our math, but a clue that we're measuring the wrong thing entirely. Picture this: you're watching a high-definition movie, but the screen's resolution has a limit. If you get too close, you'll see the pixels grainy, digital blocks where smooth images should be. The holographic universe might work the same way. At extremely small scales, space itself could pixelate, blurring the distinction between empty vacuum and the hidden information that structures it. That pixelation could act like a cosmic filter, capping the energy density of the universe in ways we're only beginning to understand. Critics argue the holographic principle is still too abstract, more mathematical poetry than testable science. But experiments are creeping closer to reality. Some quantum gravity models predict subtle fluctuations in spacetime's graininess, imperfections we might detect with ultra-precise lasers or gravitational wave observatories. Others suggest that if the universe is a hologram, there could be anomalies in the cosmic microwave background, faint echoes of its 2D origins imprinted on the oldest light in existence. Whether the holographic principle holds the answer or not, it forces us to ask deeper questions. If reality is a projection, what's projecting it? And if the missing energy isn't lost, but simply encoded in a way we can't yet measure, what else are we failing to see? The universe's greatest mysteries might not be hidden in the darkness between stars, but in the very nature of reality itself, painted on a canvas we're only learning to read. Gravity, the force that pins us to the ground and binds the cosmos together, might not be what we think it is. Forget Newton's apple or Einstein's warped spacetime for a moment. What if gravity isn't a fundamental force at all, but something far stranger, an illusion, a side effect of something deeper? That's the radical proposition of entropic gravity, a theory that flips our understanding on its head by suggesting gravity emerges from entropy, the universe's relentless march toward disorder. Picture a crowded room where everyone's constantly shifting to find space, bumping into each other, creating patterns without any central plan. Now imagine that room is spacetime itself, and those jostling bodies are bits of information at the quantum level. According to entropic gravity, what we perceive as gravity is just the statistical tendency of this system to maximize entropy, an emergent dance, not an intrinsic force. It's like watching iron filings align around a magnet and assuming the pattern is the source of the magnetism, when in reality, it's the invisible field doing the work. This idea traces back to physicist Eric Whirlwind, who in 2010 proposed that gravity could be an entropic force, a byproduct of microscopic changes in information density. Imagine stretching a rubber sheet to represent spacetime. In Einstein's general relativity, mass warps the sheet, creating gravity, but in entropic gravity, the sheet isn't being pulled, it's rearranging itself to maximize disorder, and the warp we call gravity is just the most probable outcome. The math is startlingly elegant. Equations resembling thermodynamics reproduce Newton's laws without invoking gravity as a fundamental interaction. What does this mean for dark matter? If gravity emerges from entropy, not mass, then the extra tug we attribute to invisible matter might just be our misreading of how entropy shapes spacetime on galactic scales. Galaxies rotate faster than expected not because of hidden particles, but because the information content of space itself, the way entropy distributes, creates additional, apparent gravity. It's a cosmic sleight of hand, where the universe's ledger of disorder masquerades as missing mass. Critics argue entropic gravity struggles to explain precise observations, like the bullet cluster collision, where visible matter and gravitational effects separate in ways that seem to demand dark matter's presence. But supporters counter that we might need a deeper formulation of the theory, one that accounts for entropy's behavior in extreme environments. After all, quantum mechanics once faced similar skepticism before rewriting the rules of reality. The implications ripple further. If gravity is entropic, it could unite with quantum mechanics under thermodynamics, a framework so universal it governs everything from steam engines to black holes. It also blurs the line between information and physics, suggesting the universe might fundamentally be a web of data, with forces like gravity merely its emergent language. Whether entropic gravity holds up or not, it's a reminder that sometimes the most profound breakthroughs come from asking not just how things work, but why they work that way. After centuries of treating gravity as a given, we're finally daring to ask, what if it's just the universe keeping its books balanced? What if every particle we know has a hidden twin, a mysterious counterpart lurking just beyond our detection? That's the core promise of supersymmetry, one of the most elegant theories in modern physics. It proposes a cosmic symmetry so profound, it could solve not just the mystery of dark matter, but nearly every outstanding puzzle in particle physics. Here's how it works. For every known particle, electrons, quarks, photons, there should exist a heavier superpartner with slightly different properties. Electrons would have selectrons, quarks would have squarks, and photons would have photinos. These shadow particles wouldn't just be theoretical curiosities, they'd fill the universe's missing mass, providing the perfect candidate for dark matter. The math behind supersymmetry is breathtakingly tight. It smooths out the jagged edges of quantum field theory, resolving inconsistencies that have plagued physicists for decades. Most compellingly, it predicts that the lightest superpartner, often called the neutrino, would be stable, electrically neutral, and nearly invisible to our detectors. In other words, it ticks every box for dark matter. Imagine a universe teeming with these neutrinos, drifting through galaxies like an unseen wind, their collective gravity sculpting the cosmos on scales we can't explain with ordinary matter. But there's a catch. Despite decades of searching, we've found no evidence these superparticles exist. The Large Hadron Collider, the most powerful particle smasher ever built, was supposed to be supersymmetry's grand stage. Yet after years of collisions at energies that should have produced squarks or gluinos, the detectors have come up empty. It's as if we've thrown a party for particles that never showed up. This silence has forced theorists to pivot. Some suggest superpartners are far heavier than originally thought, hiding just beyond the LHC's current reach. Others propose stealth supersymmetry, where particles decay in ways that leave almost no trace in our experiments. There's even a fringe idea called broken supersymmetry, where the symmetry isn't perfect. Superpartners exist, but they're so distorted by some ancient cosmic upheaval that they barely resemble their twins. The stakes couldn't be higher. If supersymmetry is real, it wouldn't just explain dark matter, it would bridge quantum mechanics and gravity, paving the way for a theory of everything. But with every null result, the theory's elegant equations start to feel more like a beautiful dream than a map of reality, yet many physicists aren't ready to give up. Upgraded colliders, deeper underground detectors, and even space-based experiments could still uncover hints of supersymmetry in the data. What makes this theory so captivating isn't just its potential to solve dark matter, but its audacity. It dares to suggest that everything we see is just half of a larger, hidden picture, a universe of shadows waiting to be brought into the light. Whether it's proven or disproven, supersymmetry has already reshaped how we search for answers, reminding us that sometimes the most profound truths lie in the spaces between what we know and what we've yet to discover. What if the universe's missing energy isn't missing at all, just hiding in places we can't see. Imagine folding a sheet of paper into a tiny origami crane. From a distance it looks flat, two-dimensional, but up close you notice the creases, the hidden folds where structure exists beyond what's immediately visible. Now picture our universe the same way. We perceive 3 dimensions of space: length, width, height, but what if there are more, crumpled so small they escape our notice? This isn't science fiction, it's a cornerstone of string theory, and it might explain why the energy accounting of the cosmos doesn't add up. String theory, one of the most ambitious frameworks in physics, suggests that fundamental particles aren't dots but vibrating strings. And for these strings to make mathematical sense, they need to wriggle through not just 3 dimensions, but as many as 10 or 11. Where are these extra dimensions? They could be compactified, curled up at scales a billion times smaller than an atom, like the hidden folds in that origami. But here's the twist: gravity, unlike other forces, might not be confined to our familiar dimensions. It could be leaking into these unseen layers, diluting its strength in our observable universe. That would explain why gravity feels so weak compared to electromagnetism, or the nuclear forces. It's not weak at all. We're just missing most of it, like trying to catch water in a sieve. This idea takes an even wilder turn with brain world scenarios, like the Randall-Sundrum model. Picture our universe as a 4-dimensional membrane, a brain, floating in a higher dimensional space. Ordinary matter and light are glued to our brain, trapped like insects in amber. But gravity, like a phantom, can slip off the edge, bleeding into the bulk of extra dimensions. In this model, what we call dark matter or dark energy might just be the gravitational shadow of parallel brains hovering nearby, their presence warping ours in ways we mistake for missing mass. Could we ever detect these hidden dimensions? Some experiments hunt for tiny deviations in gravity's pull at microscopic distances, where extra dimensions might tweak the inverse square law. Others look for high-energy particles at colliders that might briefly disappear into higher dimensions before snapping back, leaving trails of missing energy in detectors, echoes of the very leakage we're trying to explain. The beauty of this theory isn't just its potential to solve the dark energy puzzle, it redefines reality itself. If true, we're not just missing a fraction of the universe's energy. We're blind to the full geometry of existence, like ants crawling on a Mobius strip, unaware they're walking on a twisted loop. Whether these dimensions exist or not, the search for them reminds us that the universe's deepest secrets might not be lost, just hidden in folds we've yet to unfold. Einstein's cosmological constant, that elegant but stubborn idea that empty space has a fixed energy density, might not be so constant after all. What if dark energy isn't a static force, but something far more dynamic, ebbing and flowing over cosmic time? This is the tantalizing premise behind variable dark energy, a theory that upends our simplest assumptions and replaces them with a universe in flux. At the heart of this idea lies quintessence, a hypothetical field that permeates all of space, but unlike the cosmological constant, it can change. Imagine a cosmic pendulum, swaying between stronger and weaker repulsion, sometimes accelerating expansion, other times subtly easing off. Unlike dark energy as we know it, uniform and unchanging quintessence would interact with matter, clumping in some regions and thinning in others. It's not just a backdrop to the universe, it's an active player, shifting the rules as it goes. The implications are staggering. If dark energy varies, the fate of the cosmos might not be a slow, cold fade into emptiness. Instead, expansion could speed up, slow down, even reverse, crunching everything back together in a big bounce. Or quintessence might one day switch off entirely, freezing the universe in a static equilibrium. Some models even suggest it could mimic dark matter's effects early on, morphing into dark energy later. The universe in this view isn't just expanding, it's evolving with dark energy as its chameleon. But how do we test such a radical idea? Astronomers are turning to the universe's oldest light, the cosmic microwave background. Tiny fluctuations in this afterglow hold clues about how fast space stretched in the past. By comparing those ancient snapshots with modern measurements of supernova and galaxy clusters, scientists can hunt for inconsistencies, hints that dark energy's push wasn't always uniform. Another approach involves baryon acoustic oscillations, the fossilized ripples of sound waves from the early universe. These act as cosmic yardsticks, stretching over time in ways that betray dark energy's true nature. Quintessence isn't without its critics. Skeptics argue it's too flexible, a theory that can explain anything but predict little, yet its very adaptability might be its strength. After all, nature rarely adheres to human simplicity. Whether quintessence is real or not, it forces us to confront an unsettling possibility that the universe's missing energy isn't just hidden, but alive, shifting beneath our feet like sand in an hourglass. And if that's true, the cosmos is far stranger and far more restless than we ever imagined. Among the most terrifying possibilities in cosmology is an idea so destructive, it makes black holes look gentle phantom energy. Imagine a form of dark energy that doesn't just accelerate the universe's expansion, but does so with such ferocity that it tears apart galaxies, stars, even atoms themselves. This isn't some far-fetched sci-fi apocalypse. It's a real theoretical scenario backed by equations that keep physicists awake at night. Phantom energy takes dark energy's repulsive force and dials it up to catastrophic levels. Normally, dark energy's density stays constant as the universe expands. Think of it like a stretching rubber sheet with steady tension, but phantom energy grows stronger over time. Its density increases as space stretches, creating a runaway feedback loop. Picture blowing up a balloon that expands faster the bigger it gets, except this balloon contains everything that exists, and eventually, even the fabric of reality can't hold. The consequences are chilling. First, galaxy clusters would be wrenched apart, their gravitational bonds no match for phantom energy's accelerating push. Next, individual galaxies would unravel, stars flung into the void like sparks from a firework. Then, as the expansion rate soars beyond comprehension, planetary systems would disintegrate. Earth would be ripped from the sun's grip, followed by the sun itself torn from the Milky Way, but the horror doesn't stop there. In the final moments, even atoms, the building blocks of matter, would be shredded. Protons and electrons torn apart by the sheer force of space, stretching faster than the speed of light. The universe wouldn't just fade into cold emptiness. It would explode into absolute nothingness, a phenomenon called the Big Rip. Is this scenario plausible? The math allows it barely. Phantom energy requires a specific parameter in dark energy's equation to dip below -1, crossing a threshold where expansion becomes self-destructive. Current observations haven't ruled this out, though most data suggests dark energy's behavior is milder. Still, even a slight deviation in the future could tilt the scales toward catastrophe. Some theorists argue phantom energy could emerge if dark energy is tied to a quantum field with unstable properties, like a sled teetering at the top of a hill. Once it starts sliding, there's no stopping its accelerating descent. Others propose it might be a temporary phase, a cosmic tantrum before the field settles into a less violent state. But if it's real and persistent, the countdown to the Big Rip could already be ticking. Estimates vary wildly. Some models give the universe tens of billions of years before disintegration, others a mere few hundred million. What makes phantom energy so unsettling isn't just its destructive potential, but what it reveals about the fragility of existence. The universe's fate might hinge on a decimal point in an equation we're still struggling to solve. And that's the real lesson here, not just about doomsday scenarios, but about how much we still have to learn. The cosmos holds forces beyond our control, and sometimes understanding them means confronting the uncomfortable truth that not all mysteries have happy endings. What if spacetime, the very stage on which the universe plays out, isn't fundamental at all? What if it's more like the surface of a lake, not a static backdrop, but something that emerges from deeper, more chaotic processes beneath? This is the mind-bending premise of emergent spacetime, a theory that flips our understanding of reality on its head. Instead of treating space and time as the bedrock of existence, it suggests they're secondary phenomena, rising from something far stranger, the quantum entanglement of tiny, invisible building blocks we can't yet see. Think of it like this: when you watch a movie, you see smooth motion, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, but zoom in, and you'll find it's just a series of static frames flashing by. Emergent spacetime proposes something similar. The seamless fabric of the universe we experience might just be the visible layer of a deeper, more granular reality. At the smallest scales, there could be no space or time as we know it, just a seething network of quantum connections, like threads in a cosmic tapestry. And when enough of these threads intertwine, their collective behavior gives rise to the illusion of a continuous, flowing spacetime. The real breakthrough here comes from black holes. When physicists like Jacob Bekenstein and Stephen Hawking studied these cosmic devourers, they discovered something shocking. The information sucked into a black hole isn't lost forever. It gets encoded on the event horizon, the point of no return, in unimaginably tiny pixels. This hinted that spacetime might not be fundamental, it could be a hologram, projected from information stored at its boundaries. Fast forward to today, and researchers like Leonard Susskind and Juan Maldacena have taken this further, showing how entanglement, that spooky quantum link where particles instantly influence each other across vast distances, might actually stitch spacetime together. Picture two particles entangled in a lab. Change one and the other responds instantly, no matter how far apart they are. Now imagine this happening not just between pairs, but across an unfathomably vast web of connections. Each thread of entanglement could be like a cosmic stitch, weaving the fabric of spacetime itself. The more entangled particles are, the tighter the weave and the more solid space appears. This could explain why gravity behaves so differently from other forces. It's not a force at all, but a side effect of spacetime's emergent structure bending under the weight of entanglement. Recent experiments are starting to test these ideas. In labs around the world, physicists are simulating microscopic models of spacetime using arrays of entangled atoms or even light beams. Some are finding hints that geometric properties like distance and curvature can indeed emerge from quantum links, just as temperature emerges from the motion of molecules. It's like watching ice crystals form in reverse, not from cooling water, but from pure information tying itself into knots. Of course, not everyone's convinced. Critics argue that emergent spacetime is still too abstract, a beautiful mathematical metaphor without concrete proof. Others worry it might never be testable, leaving it stuck in the realm of philosophy. But supporters counter that every revolution in physics once seemed outlandish, from atoms to curved spacetime to quantum superposition. The universe has a habit of being stranger than we imagine, and emergent spacetime might just be the next chapter in that story. What's at stake isn't just a new theory of gravity or a fix for dark energy, it's the very nature of reality. If spacetime emerges from entanglement, then the universe isn't a collection of objects floating in space, it's a vast, dynamic network of relationships, where here and now are illusions woven from deeper connections. And that changes everything, from the fate of black holes to the origins of the Big Bang. Emergent spacetime could rewrite the rules, not by adding new pieces to the puzzle, but by revealing that the puzzle itself was never what we thought it was. Einstein's theory of general relativity paints a vivid picture of our universe, space and time woven into a single, dynamic fabric, warped by matter and energy. But zoom in far enough and the picture starts to crack. At the heart of black holes and the beginning of the Big Bang, the equations break down. predicting infinities called singularities, points where gravity becomes infinitely strong and the laws of physics simply give up. Most physicists see these as red flags, signs that relativity is incomplete, but what if there's a way to fix the math before it breaks? That's where loop quantum cosmology comes in, reimagining the universe at the smallest scales in a way that might rewrite our understanding of dark energy itself. Loop quantum cosmology is the cosmic cousin of loop quantum gravity, a theory that treats spacetime not as smooth and continuous, but as a woven tapestry of tiny, discrete loops. Think of it like pixels on a screen, but for reality itself. At the quantum level, these loops form a network so fine, it's invisible to us, just as a tapestry looks smooth from a distance. But this pixelation isn't random, it follows strict quantum rules, meaning space can't be squeezed into an infinitely tiny point. Instead, there's a smallest possible volume, a quantum graininess that stops singularities in their tracks, no infinite densities, no spacetime tears. Just a universe that bounces rather than breaks. This changes everything about how we picture the Big Bang. Instead of a fiery singularity where time begins, loop quantum cosmology suggests a big bounce. Imagine the universe not as a single explosive origin, but as a cycle contracting to a tiny, but finite size before rebounding outward. It's like squeezing a spring, push too hard and it pushes back. In this model, dark energy might not be a mysterious force injected into the universe, but a relic of that bounce, a quantum echo left over from the moment spacetime hit its smallest possible size and recoiled. But how does this impact dark energy today? Here's where things get even wilder. Quantum corrections in loop cosmology tweak Einstein's equations, subtly altering how gravity behaves on cosmic scales. Some models suggest these tweaks could mimic dark energy's effects, accelerating expansion without needing an exotic substance. Others propose that dark energy isn't constant, it could fade or fluctuate as the universe evolves, tied to the quantum geometry of spacetime itself. Picture a rubber band stretching. At first it resists, but over time its tension changes. If spacetime has a similar quantum tension, dark energy might not be a fixed feature of the cosmos, but a phase in its life cycle. Testing these ideas isn't easy, but there are clues. If the universe really bounced, traces of its pre-Big Bang past might linger in the cosmic microwave background, subtle patterns in the oldest light we can see. Some researchers hunt for anomalies in this ancient glow, like faint swirls or unexpected gaps in temperature, that could hint at a quantum spacetime fabric. Others look for deviations in how galaxies cluster over time, searching for signs that gravity's grip weakens or strengthens in ways loop quantum cosmology predicts. The brilliance of this theory isn't just in fixing singularities, it's in daring to ask what spacetime truly is. For centuries, we've treated it as a static stage. But if loop quantum cosmology is right, the stage itself is alive, woven from threads of quantum connection, pulsing with energy we're only beginning to decode. Whether it's the final answer or just a step toward one, it reminds us that sometimes the universe's biggest secrets hide in the smallest stitches. Imagine building the universe not from equations or particles, but from tiny geometric building blocks, like cosmic Legos snapping together to form spacetime itself. That's the essence of causal dynamical triangulation, a radical approach to quantum gravity that rewrites the rules by constructing reality from the ground up. Forget smooth, continuous space. Here, the fabric of existence is a patchwork of microscopic triangular chunks, each a fundamental piece of the puzzle. And hidden in the angles and edges of these pieces might lie the answer to the universe's missing energy. The idea is deceptively simple. Start with the smallest possible units of spacetime, four-dimensional pyramids called pentacorons, and let them combine according to strict rules. Each piece must fit causally, meaning time always flows forward, never looping back on itself. No wormholes, no time travel, just a universe that assembles itself one deterministic step at a time. The magic happens when you throw enough of these chunks into the mix. At large scales, their collective behavior mimics the smooth spacetime we know, while at the quantum level, they reveal a bubbling, fractal structure. It's like zooming in on a photograph. From afar, it's a seamless image, but up close, you see the pixels, and in this case, the pixels are the building blocks of reality. But how does this connect to dark energy? Here's where geometry takes center stage. In causal dynamical triangulation, the way these blocks fit together determines the curvature of spacetime. Some configurations naturally create positive curvature, mimicking the effects of dark energy's repulsive push. Others might cancel it out entirely, by tweaking the rules of assembly, adjusting the glue that binds these pieces. Researchers can simulate universes with different energy balances. In some models, the sheer number of possible configurations at the quantum level generates an effective dark energy, not as an exotic substance, but as a statistical byproduct of spacetime's granularity. Think of it like a foam of soap bubbles. Each bubble is a tiny, discrete unit, but together they create a surface with emergent properties, tension, elasticity, even ripples. In the same way, the quantum foam of spacetime could generate dark energy as a collective effect, a cosmic tension arising from the way the universe stitches itself together. This would mean the missing energy isn't missing at all, it's baked into the geometry of existence, hidden in the folds between the triangles. Of course, there are skeptics. Some argue the theory is too abstract, a mathematical playground without experimental consequences, but supporters point to surprising successes like how causal dynamical triangulation naturally avoids the singularities that break general relativity, or how it reproduces Einstein's equations at large scales without assuming them from the start. And while we can't yet probe spacetime at this granular level, future experiments with quantum sensors or gravitational wave detectors might look for telltale signatures, tiny deviations from smoothness that betray the universe's blocky foundations. What makes this approach so compelling isn't just its potential to solve dark energy, but its sheer audacity. It doesn't just tweak gravity or add new particles, it rebuilds reality from scratch, showing how the cosmos might emerge from the humblest of parts. Whether it's the final answer or a stepping stone, causal dynamical triangulation reminds us that sometimes the universe's deepest secrets are hiding in plain sight, not in the vastness of space, but in the smallest stitches of its fabric. Some of the universe's strangest secrets might be hiding in plain sight not as particles, but as something even more elusive, unparticles. This speculative idea, born from the edges of theoretical physics, suggests entire sectors of reality could exist beyond our standard model, invisible yet exerting a ghostly influence on the cosmos. Unlike familiar particles with definite masses and properties, unparticles behave in ways that defy conventional classification. They don't fit neatly into the particle zoo we know: electrons, quarks, photons, but instead operate under a bizarre principle called scale invariance, meaning they look the same no matter how close or far you zoom in. Picture a fractal pattern repeating endlessly, where each level reveals the same intricate design. That's the essence of unparticles, a form of matter or energy that doesn't play by the usual rules of scale. The concept first emerged in 2007, when physicist Howard Georgi proposed that hidden sectors of particles could interact so weakly with our world that they'd appear to lack mass altogether. These unparticles wouldn't behave like discrete objects, but more like smeared-out clouds of influence, their effects rippling across spacetime in ways that resemble fractional dimensions. Imagine tossing a stone into a pond, but instead of clean circular waves, the ripples split into fractured, uneven patterns, as if the water itself couldn't decide how to transmit the energy. That's the kind of anomaly unparticles could introduce into the fabric of reality. How does this connect to dark energy? If unparticles exist, Their scale-invariant nature means they wouldn't dilute as the universe expands. Ordinary matter thins out over time, but unparticles could maintain a constant density, their influence persisting like an eternal echo. Some models suggest this could mimic dark energy's repulsive force, driving cosmic acceleration without invoking a cosmological constant. Others propose that unparticle-mediated interactions might subtly tweak gravity at vast distances, altering how galaxies cluster or how light bends around empty space. The real challenge lies in detecting something that, by definition, resists confinement. Unlike WIMP or axions, unparticles wouldn't leave sharp signals in particle colliders or underground detectors. Instead, scientists hunt for indirect clues, anomalies in the way particles decay, subtle shifts in gravitational waves, or unexpected patterns in the cosmic microwave background. Even the Large Hadron Collider has scoured its data for hints of unparticle interference, like searching for whispers in a hurricane. What makes this theory so captivating isn't just its potential to explain dark energy, it's the way it forces us to rethink the boundaries of physics. Unparticles blur the line between matter and energy, between the granular and the continuous. They remind us that the universe's missing pieces might not be hiding in the shadows of what we know, but in the uncharted territories of what we've yet to imagine. And if they're out there, they could rewrite not just the story of dark energy, but the very definition of reality itself. What if one of physics' most sacred constants, the speed of light, isn't so constant after all? For over a century, Einstein's theory of relativity has treated light speed as an unwavering cosmic speed limit, approximately 300,000 kilometers per second in a vacuum, never faster, never slower. But a handful of physicists are daring to challenge this pillar of modern science, proposing something radical: that light may have raced across the infant universe at breakneck velocities before slowing to its current pace. If true, it wouldn't just rewrite cosmology textbooks, it could overhaul our entire understanding of the universe's missing energy. This idea, known as variable speed of light cosmology, flips the script on dark energy. Instead of invoking mysterious forces or invisible substances, it suggests that discrepancies in cosmic energy budgets might stem from miscalibrating light's primordial speed. Picture the early universe as a dense, seething plasma where photons struggle to travel freely, like someone wading through a packed crowd. If light moved faster back, then even briefly it would alter how energy propagated, potentially explaining why today's universe appears to lack the mass it should have. The math is provocative: tweak light's early speed and suddenly, the need for dark energy might vanish entirely. But how could such a fundamental constant change? Some models propose that light's speed was tethered to the temperature of the young cosmos, slowing as space expanded and cooled. Others suggest deeper modifications to relativity itself, where the fabric of spacetime had different elastic properties in its infancy. Imagine stretching a rubber band; the tension changes as it expands. Similarly, the universe's underlying physics might have stretched over time, with light speed acting like a cosmic odometer, recording the shift. The catch: observational evidence pushes back hard. The cosmic microwave background, the afterglow of the Big Bang, serves as a meticulous time capsule, its patterns exquisitely sensitive to light's behavior. So far, it aligns with standard relativity, leaving little room for dramatic variations in light speed. Even more damning, the spectra of distant quasars, ancient beacons whose light has traveled billions of years, show no detectable shift in the fine structure constant, a parameter intimately tied to light's velocity. It's as if the universe has left a paper trail, and every page insists the speed limit hasn't budged, yet the theory persists, buoyed by stubborn gaps in our knowledge. Proponents argue that subtle variations in light speed could still lurk beneath observational thresholds, or that our tools aren't yet precise enough to catch them. Some even speculate that light's speed didn't vary smoothly but in abrupt quantum jumps, leaving fleeting imprints we've yet to decipher. Whether variable light speed holds up or not, its boldness is exhilarating. It forces us to question whether the constants we cling to are truly immutable, or if they're just the current settings in a cosmos that's still revealing its rules. And in that uncertainty lies the real thrill of science, not just solving mysteries, but daring to redefine the questions themselves. What if every particle in the known universe has a doppelganger, a perfect mirror copy lurking just beyond our perception? This is the startling premise behind mirror matter theory, which proposes that dark matter might be nothing more than a hidden twin of ordinary matter, obeying identical physical laws but invisible to our detectors. The idea stems from one of nature's most elegant principles, symmetry. Just as your left and right hands mirror each other, the universe itself might possess a parallel sector where particles are flipped versions of our own same masses, same forces, but completely oblivious to our existence. This mirror world wouldn't just be a theoretical curiosity. If real, it could solve the dark matter enigma with breathtaking simplicity. Imagine a proton's mirror counterpart drifting through your body right now, feeling the tug of mirror gravity from mirror stars and mirror galaxies, all occupying the same space as our familiar cosmos, yet barely interacting. The only shared force between these parallel realms, gravity. That's why we'd see the gravitational effects of mirror matter clumping around galaxies, while light and other signals slip past us unnoticed. It's like living in a house haunted by ghosts who rearrange the furniture but refuse to speak. The roots of this theory stretch back to the mid-20th century, when physicists noticed baffling asymmetries in particle behavior. Certain quantum interactions seem to prefer one direction over another, violating what was once thought to be nature's perfect mirror symmetry. To restore balance, theorists propose that somewhere, a hidden mirror version of these processes must exist, an idea that snowballed into entire mirror sectors. Over time, scientists realized these shadow particles wouldn't just fix symmetry, they could fill the universe's missing mass without inventing exotic new physics. Detecting mirror matter, however, is like trying to shake hands with a reflection. Since mirror photons don't interact with our eyes or telescopes, we'd never see their galaxies. Even if a mirror planet passed through Earth, the only sign might be a fleeting gravitational tremor. Some experiments hunt for these ghostly interactions, ultra-sensitive detectors buried deep underground, waiting for mirror particles to nudge ordinary atoms. Others look for cosmic anomalies, like stars that mysteriously brighten as invisible mirror objects pass in front, yet mirror matter faces fierce challenges. If these particles truly mirror ours, they should have mirror chemistry, mirror planets, even mirror life, raising the eerie possibility of invisible civilizations sharing our space. More critically, precise measurements of neutron behavior suggest mirror sectors would need slight asymmetries to match observations, muddying the theory's elegant symmetry. Whether mirror matter exists or not, it forces a profound question: how many layers of reality are we missing? The universe loves symmetry, and the idea that we're only seeing half the picture, that every quark, every electron has a silent twin, is as humbling as it is thrilling. Somewhere beyond our perception, an entire cosmos might be unfolding in lockstep with our own, its secrets written in the very gravity that binds us both. What if the universe's expansion isn't driven by some mysterious dark energy, but by matter that weighs less than nothing, negative mass? The idea that particles could exist with inverted properties, where gravity pushes instead of pulls, is one of the most bizarre and controversial theories in cosmology. Picture dropping a ball and watching it shoot upward instead of falling, or a car accelerating backward when you hit the gas. That's the world negative mass would create, and if it exists, it could rewrite our understanding of cosmic acceleration without invoking dark energy at all. The math behind negative mass is surprisingly straightforward, at least on paper. In Einstein's equations, mass is just a number, and nothing stops that number from being negative. Flip the sign and gravity becomes repulsive. A universe peppered with such matter would naturally push itself apart, mimicking the effects we attribute to dark energy. Some models even suggest negative mass could form invisible, cosmic scaffolding, with regions of repulsive gravity counteracting the pull of ordinary matter, perfectly balancing the equations that currently demand dark energy's existence. But there's a catch: negative mass comes with stability issues that make physicists wince. Ordinary matter with positive mass tends to clump together under gravity, forming stars and galaxies. Negative mass would do the opposite, repelling itself and fleeing from positive mass, creating a chaotic, ever-expanding foam. Recent computer simulations, however, reveal a loophole. If negative mass is distributed in a specific, uniform way like a fine mist permeating space, it might avoid these instabilities, gently counteracting gravity's pull without tearing the cosmos apart. The real shock came in 2018, when a team of researchers published simulations showing how negative mass could actually reproduce observed galactic rotation curves, no dark matter required. Their models demonstrated that a diffuse halo of negative mass around galaxies would bend light and speed up stars at the edges, just as dark matter is thought to do. It's a radical two-for-one solution, one exotic substance potentially explaining both dark matter and dark energy's effects. Skeptics aren't convinced. Negative mass violates energy conditions that underpin much of modern physics, and no such particles have ever been detected, yet proponents argue that absence of evidence isn't evidence of absence, especially when we're hunting for something that, by definition, would avoid interaction. Some even speculate negative mass might hide in plain sight, camouflaged as quantum fluctuations or hidden within the structure of spacetime itself. Whether negative mass is a groundbreaking insight or a mathematical mirage, it forces us to confront a profound question: are we missing an entire class of matter, one that bends the rules of reality as we know it? In a universe that's already proven far stranger than we imagined, perhaps the most unsettling possibility isn't that dark energy exists, but that we've been overlooking a shadow world where gravity runs backward. At the heart of gravity's deepest mystery lies a quantum whisper, the graviton, a hypothetical particle believed to transmit the force that holds the cosmos together. But what if these invisible messengers aren't just fleeting carriers of gravity? What if, under the right conditions, they could clump together into an exotic quantum state, saturating the vacuum of space with an energy so pervasive it drives the universe apart? This is the daring idea behind graviton condensate theory, where dark energy emerges not from some alien substance, but from gravity itself turning inside out. To grasp how this works, picture a crowd of people scattered randomly in a room, each representing a single graviton. Now chill that room to near absolute zero. Suddenly, the individuals merge into a unified wave, moving as one superentity. This is a Bose-Einstein condensate, a state of matter where quantum weirdness dominates and particles lose their individuality. Apply this to gravitons permeating spacetime, and you get a cosmic condensate, a seamless, universe-filling medium where these gravity-carrying particles act collectively, generating a gentle, repulsive pressure. It's as if gravity, stretched thin across the expanding cosmos, phases into a new form, one that pushes rather than pulls. The math behind this is rooted in quantum field theory's most sophisticated tools. In curved spacetime, gravitons wouldn't just flit between masses like Newton's apple tree messengers. Their behavior would be shaped by the universe's expansion, with wavelengths stretching over eons. Under extreme conditions like the cold, sparse depths of interstellar space, these stretched gravitons could theoretically undergo Bose-Einstein condensation, their quantum waves overlapping until they behave as a single coherent field. The energy density of this condensate, remarkably similar to the observed value of dark energy, but here's the twist: this isn't just abstract number crunching. The theory makes testable predictions. If graviton condensates exist, they'd subtly alter how gravitational waves propagate across the cosmos. Future observatories, like the proposed laser interferometer space antenna, might detect anomalies in the ripples from colliding black holes, hints that gravity waves are interacting with this invisible quantum substrate. There's even a wilder implication. If the condensate's density changes over time, dark energy's strength could vary, meaning the universe's acceleration might not be set in stone. Critics point out the elephant in the room: we've never directly detected gravitons, let alone observed them condensing, yet proponents argue that absence doesn't mean impossibility. After all, superconductivity, a similarly bizarre quantum collective effect, was once dismissed as fantasy before revolutionizing technology. The universe has a knack for realizing the seemingly impossible. What makes this theory so compelling isn't just its audacity, but its economy. It doesn't invent new particles or forces. Instead, it repurposes gravity's own building blocks, revealing how the same phenomenon that binds stars could, under quantum rules, also tear space apart. In a cosmos full of shadows, sometimes the darkest secrets are hiding in the lightest particles of all. Imagine the universe just moments after the Big Bang, a seething, chaotic plasma cooling rapidly as space expands. In that frenzy, cracks could have formed in the very fabric of reality, like ice fissuring as it freezes. These flaws, known as cosmic strings, aren't made of matter or energy as we know them. They're ultra-dense, thread-like defects in spacetime itself, infinitely thin, yet so massive that a single inch could weigh more than Mount Everest. Stretching across the cosmos for billions of light years, these relics from the universe's birth might be weaving through the void right now, shaping the distribution of dark matter in ways we're only beginning to understand. Unlike black holes, which curl spacetime into singularities, cosmic strings would be more like scars, linear distortions where the rules of physics twist slightly. Picture a tablecloth wrinkled by an invisible thread beneath it. Galaxies near a cosmic string might appear duplicated or distorted, their light bent around these unseen filaments. Some models suggest networks of strings could act as gravitational scaffolding, tugging dark matter into the vast, web-like structures we observe today. And because they'd barely interact with light or ordinary matter, their presence would be felt only through their gravity, making them perfect shadow contributors to the universe's missing mass. What sets cosmic strings apart from other exotic dark matter candidates is their origin, their topological defects, a category that includes other theoretical oddities like domain walls and monopoles. Think of these defects as cosmic knots tied during the universe's phase transitions, like bubbles forming in cooling lava, each with boundaries that trap energy. While domain walls would be two-dimensional sheets and monopoles point-like particles, strings strike a delicate balance, massive enough to influence galaxies, yet sparse enough to avoid crashing into each other constantly. Simulations show that a single string looping through a galaxy could subtly alter the orbits of stars, mimicking the effects of a dark matter halo without requiring new particles. The hunt for cosmic strings has led researchers to scrutinize some of the universe's most precise natural clocks, pulsars. These spinning neutron stars emit radio waves with metronomic regularity. If a string passed between Earth and a pulsar, the spacetime warp would briefly disrupt the timing of those pulses, like a finger plucking a guitar string. Astronomers have also scoured the cosmic microwave background for telltale temperature spikes, sharp edges in the afterglow of the Big Bang that strings might leave behind. So far, no definitive evidence has surfaced, but the search continues with increasingly sensitive instruments. Even if cosmic strings remain elusive, their theoretical allure persists. They bridge particle physics and cosmology, offering a glimpse into the universe's most violent epoch, while potentially solving one of its greatest mysteries. Whether they are out there or not, they remind us that the answers to dark matter might not lie in new particles, but in ancient wrinkles etched into spacetime itself, a cosmic fossil record waiting to be read. Every atom in your body, every star in the sky, every shred of matter we can see exists because of a cosmic fluke, an unimaginably tiny imbalance in the early universe where matter barely edged out antimatter. For every billion particles of antimatter created in the Big Bang's fury, there were 1,000,001 particles of matter. That 1 in a billion surplus is all we are. But what if this lopsidedness, this Barrian asymmetry, isn't just a quirk of particle physics? What if it's intimately tied to the universe's most elusive ingredient, dark energy? The connection hinges on a process called effulgdyne baryogenesis, a theory that rewinds cosmic history to when the universe was less than a trillionth of a second old. Picture a quantum field not unlike the Higgs field that gives particles mass, but one that could tip the scales between matter and antimatter. As the infant cosmos cooled, this field could have settled into a lopsided state, like a ball rolling down a hillside and landing slightly off-center. That tiny tilt would have favored matter's creation, imprinting the universe with the asymmetry we see today. But here's the twist: such fields wouldn't just influence particle physics. Depending on how they decay, they could leave behind a residual energy that permeates space itself, a cosmological constant eerily similar to dark energy. Think of it like pouring syrup onto pancakes. The initial uneven spread creates patterns, thick pools here, thin streaks there. In the cosmos, the effulgdyne mechanisms, syrup, might have clumped matter into galaxies while leaving behind a diffuse, lingering sweetness, dark energy. The math even suggests these fields could have undergone phase transitions, like water freezing into ice, locking in both the matter-antimatter split and dark energy's repulsive force simultaneously. Critics argue this theory stretches plausibility, requiring fine-tuned initial conditions that border on miraculous, yet supporters counter that the universe's existence already hinges on improbable balances, from the precise strength of gravity to the mass of the electron. If nature conspired to favor matter over antimatter, why couldn't that same conspiracy seed dark energy too? Some models go further, proposing that dark energy isn't static but a dynamical echo of that primordial imbalance, its strength waxing or waning as the universe evolves. The implications are staggering. If Barrian asymmetry and dark energy share roots, we're not just solving two puzzles at once, we're uncovering a hidden link between the universe's first moments and its ultimate fate. It's a reminder that the cosmos' greatest mysteries might not be separate at all, but threads of the same grand design, woven together in ways we're only beginning to trace. Black holes, the universe's ultimate cosmic vacuums, might be hiding a secret far stranger than anything we've imagined. What if these gravitational monsters aren't just consuming energy, but somehow generating it? A groundbreaking theory suggests that supermassive black holes could be the hidden engines behind dark energy, their insatiable growth tied to the accelerating expansion of the cosmos itself. This idea hinges on a phenomenon called vacuum decay. Picture empty space not as true nothingness, but as a seething quantum foam where particles flicker in and out of existence. According to quantum field theory, this vacuum has an intrinsic energy, and under extreme conditions, like those near a black hole's event horizon, that energy can shift states, releasing latent power. Recent studies propose that as supermassive black holes gorge on matter and merge, they might trigger localized vacuum decay events, tapping into this quantum reservoir. The result, a net gain in energy that doesn't just stay trapped in the black hole, but spills outward, pushing space itself apart. Galaxy surveys are adding fuel to this fire. Observations from projects like the Sloan Digital Sky Survey reveal a puzzling correlation. The faster a galaxy's central black hole grows, the stronger the dark energy influence in its vicinity seems to be. It's as if these cosmic behemoths are somehow charging up the fabric of spacetime around them. Even more intriguing, models suggest that the combined output of all supermassive black holes in the universe could match the observed value of dark energy's repulsive force, not as a coincidence, but as a direct consequence. Critics argue this theory demands exotic physics, like black holes violating energy conservation in ways we've never observed, yet proponents counter that quantum fields near singularities already defy classical intuition, and that vacuum decay, while speculative, is mathematically plausible. If true, it would mean dark energy isn't some separate, mysterious substance, but the cumulative breath of black holes exhaling quantum energy into the cosmos. The implications are staggering. A universe where black holes drive expansion would age very differently, their influence waxing as they merge and grow, potentially dooming galaxies to isolation long before the stars within them burn out. It's a haunting vision, but one that reminds us, the darkest objects in the cosmos might hold the brightest keys to understanding it. Neutrinos are the ghosts of the particle world, shy, nearly massless, and so reluctant to interact that trillions pass through you every second without a trace. But what if these cosmic wallflowers are secretly pulling the strings of the universe? A daring theory suggests that neutrinos, with their peculiar ability to shift masses over cosmic time, could be the hidden architects of dark energy's relentless push. At the heart of this idea lies the neutrino seesaw mechanism, one of particle physics' most elegant puzzles. Neutrinos come in three known flavors: electron, muon, and tau, and they oscillate between these states as they travel. But here's the twist: their masses aren't fixed. Quantum effects could cause them to grow heavier or lighter depending on the energy of their surroundings. Picture a cosmic teeter-totter. As the universe expands and cools, the balance tips, and neutrinos that were once nearly massless might gain weight, while others slim down. This dance of shifting masses isn't just a curiosity, it could be injecting energy into the vacuum of space itself. How the math gets intricate, but the gist is this: if neutrinos interact with a hypothetical field permeating the cosmos, something akin to the Higgs field, but far subtler, their mass fluctuations could transfer energy into that field, creating a repulsive effect. It's like blowing up a balloon with tiny, rhythmic puffs of air. Each neutrino's mass shift would contribute a minuscule push, but collectively, over billions of years, they might fuel the universe's accelerating expansion. The implications are staggering. Unlike traditional dark energy models, which rely on a static cosmological constant, neutrino dark energy would be dynamic, evolving alongside the cosmos. Early in the universe's history, when neutrinos were hotter and more energetic, their influence would have been muted, but as space stretched and cooled, their impact could have grown, explaining why cosmic acceleration seems like a recent phenomenon in galactic terms. Critics point out gaps. Neutrinos as we know them are too lightweight to account for all of dark energy's effects unless there's a fourth, sterile neutrino lurking in the shadows, far heavier than its siblings. Experiments like Fermilab's short baseline neutrino program are hunting for hints of such a particle, but so far, the evidence is elusive. Others argue that even with sterile neutrinos, the energy budget doesn't quite add up without additional exotic physics. Yet the theory's elegance keeps it alive. It ties together two of physics' greatest mysteries, dark energy and neutrino mass, without inventing entirely new forces or particles. And it offers testable predictions. If neutrino dark energy is real, subtle anomalies should appear in the way galaxies cluster, or how the cosmic microwave background's patterns skew over time. Whether neutrinos hold this cosmic secret or not, the idea itself is a reminder that sometimes the universe hides its most profound truths in the quietest places. Not in blazing quasars or colliding black holes, but in the whisper-light passage of particles so faint, we're only beginning to sense their gravity. Gravity as we know it plays by strict cosmic rules, its influence limited by the speed of light, radiating outward in orderly ripples through spacetime. But what if those rules aren't as rigid as Einstein imagined? Non-local gravity theories propose something radical, that gravity's reach isn't bound by light's speed limit. Instead, its effects could stretch across the universe instantaneously, like a hidden web connecting distant galaxies in ways our current physics can't explain. This isn't just a tweak to relativity, it's a full rewrite of how we understand one of the universe's fundamental forces, with staggering implications for the missing energy problem. At the heart of non-local gravity is a simple but profound shift in perspective. In Einstein's framework, gravitational changes propagate at light speed. If the sun vanished right now, Earth wouldn't feel the loss for about 8 minutes. Non-local models discard this constraint, allowing gravity to teleport its influence across vast distances without delay. Picture throwing a stone into a pond, but instead of watching waves spread outward, the entire surface ripples all at once. This instantaneous connection could arise from quantum entanglement, like links woven into spacetime itself, where separated regions remain mysteriously synchronized. Why would this matter for dark energy? If gravity operates non-locally, its equations gain extra terms, corrections that mimic the effects of an invisible repulsive force. These corrections aren't arbitrary. They emerge naturally from the math when you allow gravitational fields to remember past states or anticipate future ones. It's as if spacetime has a kind of cosmic inertia, resisting rapid changes in curvature in ways that look, on large scales, exactly like dark energy's push. Suddenly, the accelerating expansion of the universe isn't driven by some mysterious substance, it's gravity itself, behaving in ways we're only beginning to decode. Testing these ideas isn't easy, but astronomers have clever workarounds. One approach studies binary pulsars, pairs of neutron stars orbiting each other with atomic clock precision. If gravity is truly non-local, their orbits should decay slightly differently than general relativity predicts, as if tugged by invisible threads connecting them to distant masses. Another tactic involves the cosmic microwave background subtle irregularities. Non-local gravity would imprint distinct patterns on this ancient light, like fingerprints left by a force that doesn't play by light speed rules. So far, the data remains inconclusive, but next-generation telescopes like the Euclid Space Observatory could finally spot these telltale signs. The boldest versions of non-local gravity go even further, suggesting that black holes might be the ultimate non-local engines. Their event horizons, already known to scramble information, could act as cosmic conduits, linking disparate parts of the universe through hidden quantum channels. If true, the missing energy we've been chasing might not be missing at all, just temporarily stored in these non-local connections, like a galaxy-spanning battery we've yet to learn how to measure. Skeptics argue this all sounds perilously close to magic, invoking unseen links without definitive proof, but history shows that radical ideas often precede breakthroughs. Quantum entanglement itself was once dismissed as spooky action at a distance before becoming a cornerstone of modern physics. Whether non-local gravity survives scrutiny or not, it forces us to confront a humbling possibility that the universe's deepest workings might not just be stranger than we imagine, but stranger than we can imagine. And sometimes the most revolutionary answers begin by questioning the very rules we've taken for granted. Black holes aren't just cosmic vacuum cleaners, they're the ultimate shredders of information, or at least that's what we used to think. According to Hawking's famous calculations, anything that falls into a black hole is lost forever, its details scrambled into meaningless thermal noise. This idea, known as the information paradox, has haunted physicists for decades, but what if the solutions to this paradox don't just save quantum mechanics? What if they're secretly tweaking the universe's energy budget in ways we've overlooked? One radical fix involves firewalls, searing walls of energy just inside the event horizon that burn up incoming matter before it reaches the singularity. Think of it like a cosmic incinerator lining the edge of a black hole, ensuring no information ever makes it to the point of no return. At first glance, this seems like a desperate patch, but the implications run deep. If firewalls exist, they'd radiate energy outward, subtly contributing to the vacuum's background hum. Over billions of years, that energy could accumulate, nudging the universe's expansion in ways that mimic or even replace dark energy's effects. It's a long shot, but the math hints at a tantalizing connection. The same quantum corrections that resolve the information paradox might also tweak gravity's behavior on cosmic scales. Then there's the holographic principle, which suggests black holes don't destroy information at all, they encode it on their surfaces like cosmic hard drives. If true, the energy required to maintain this cosmic ledger could have ripple effects far beyond the event horizon. Imagine spacetime as a stretched rubber sheet. Every bit of information stored on a black hole's surface might create tiny dimples in the fabric, collectively altering how the universe expands. Some models even suggest this could explain why dark energy's density is so eerily fine-tuned. It's not a mysterious substance, but the cumulative effect of countless black holes, remembering the universe's history. But the wildest twist comes from entanglement entropy. When particles near a black hole become entangled with its interior, their quantum links stretch like taffy, generating energy that counteracts gravity's pull. This isn't just theoretical. Calculations show these quantum tensions could produce repulsive forces eerily similar to dark energy. It's as if every black hole is quietly exhaling a breath of anti-gravity, woven from the threads of broken quantum connections. Scale this up to all the supermassive black holes in the universe, and suddenly, cosmic acceleration starts to look less like a mystery and more like a side effect of quantum mechanics fighting to preserve information. Of course, not everyone's convinced. Critics argue these ideas are too speculative, stitching together disparate puzzles with mathematical duct tape. Yet the audacity of the premise is undeniable. The same physics that saves information from oblivion might also hold the key to the universe's runaway expansion. Whether firewalls, holograms, or quantum threads win out, one thing's clear: black holes aren't just devouring matter, they might be quietly shaping the fate of everything. Imagine the entire universe as a cosmic hard drive, where every star, planet, and particle is just a projection of data stored on a distant, two-dimensional surface. This is the essence of the holographic principle, a mind-bending idea that our three-dimensional reality might be nothing more than an illusion, like a movie playing on the walls of an unimaginably vast theater. But what if this principle doesn't just redefine space and time? What if it also holds the key to dark energy's relentless push, tying the universe's accelerating expansion directly to the fundamental limits of information itself? That's the radical promise of holographic dark energy, a theory that merges two of physics' deepest puzzles into one elegant solution. At the heart of this idea lies a simple but profound constraint: the universe has a finite amount of information it can contain, governed by the size of its boundaries. Just as your smartphone can't store infinite photos, space itself has a cosmic data limit, a maximum number of bits that can describe any given region. The holographic principle suggests this limit isn't tied to volume but to surface area. Think of it like a hologram on your credit card. The shimmering 3D image emerges from a flat, 2D surface, with its complexity capped by the pixels available. Apply this to the cosmos, and suddenly, the vacuum of space isn't truly empty, it's saturated with information, and that information has energy. Here's where dark energy enters the picture. As the universe expands, its boundary grows, increasing the total information capacity, but there's a catch: the energy density of this holographic information must decrease to stay within cosmic limits, like thinning out paint to cover a larger canvas. The math reveals something astonishing: this adjustment naturally produces a repulsive force. accelerating expansion in precise agreement with observed dark energy effects. It's as if the universe, in trying to balance its information budget, inadvertently fuels its own runaway growth. The implications are staggering. Unlike traditional dark energy models, which treat it as an arbitrary constant, holographic dark energy links cosmic acceleration to something far more fundamental: the universe's inherent information structure. This connection even predicts how dark energy's strength should evolve over time. Early in cosmic history, when the universe was smaller, its holographic energy density would have been higher, subtly influencing galaxy formation. Today, as space stretches toward infinity, that influence wanes but never quite vanishes, leaving just enough push to match our observations. Critics point out gaps. The theory struggles to explain why the holographic scale, the precise size at which information limits kick in, aligns so perfectly with the observable universe's horizon. Others argue it's too abstract, lacking the concrete hooks that make particle-based dark matter theories testable, yet supporters counter that its elegance is its strength. By unifying information theory and cosmology, holographic dark energy doesn't just solve a puzzle, it reshapes how we frame the questions themselves. The most tantalizing clue might lie in the cosmic microwave background. If holographic dark energy is real, its unique information constraints should imprint subtle irregularities in this ancient light patterns, distinct from those left by conventional dark energy. Upcoming telescopes like the Simons Observatory are scanning for these very fingerprints, hunting for echoes of a universe where information isn't just stored, but actively shapes the fate of everything. Whether the holographic principle ultimately unlocks dark energy's secrets or not, it forces a profound shift in perspective. The universe's greatest mysteries might not be hidden in unseen particles or forces, but in the invisible ledger of information that underlies reality itself. And if that's true, the answers we seek could be written not in the stars, but in the cosmic code that projects them. What if the universe's missing energy isn't a mystery of physics, but a glitch in the code of reality itself? Enter the simulation hypothesis, the provocative idea that our entire cosmos might be an advanced computational construct, and dark energy just an optimization trick to save processing power. It sounds like science fiction, but some physicists aren't laughing it off entirely. Imagine a video game rendering distant galaxies at lower resolution to conserve memory. Could the universe's accelerating expansion be a similar shortcut, a cosmic load balancing act by whatever or whoever is running the simulation? The logic is eerily compelling. In a simulated reality, rendering every atom in real time would demand unimaginable computational resources, so why not cut corners? By tweaking the parameters of empty space, making it repulsive on large scales, the simulation could avoid calculating trillions of unnecessary gravitational interactions between distant galaxies. Dark energy, in this view, isn't a force but a feature, like fog in a game masking distant terrain to spare the graphics card. Even the infamous cosmological constant, that elusive number governing dark energy's strength, starts to make sense. It's not finely tuned for life, but for efficiency, set to the minimum value needed to keep the simulation running smoothly. But before we dismiss this as philosophical whimsy, consider the testable implications. If we're in a simulation, the universe might reveal its digital skeleton at the smallest scales. Just as pixels betray a screen's resolution, spacetime itself could pixelate if you zoom in far enough. Some quantum gravity models predict exactly this, a granularity to reality at the Planck scale, where smooth geometry breaks into jagged quanta. Experiments hunting for these spacetime pixels using ultra-precise lasers or particle colliders are, in effect, probing for the universe's source code. Then there's the lookup table argument. Simulated worlds often precompute certain outcomes to save processing cycles. If our physics constants like the speed of light or the strength of gravity are hard-coded values rather than emergent properties, they might contain hidden mathematical artifacts. Astronomers have scoured the cosmic microwave background for signs of these fingerprints, repeating patterns, or anomalies that suggest underlying computation. So far, the universe's data looks organic, but the search continues. Critics rightfully caution that the simulation hypothesis skirts the edge of pseudoscience. Unlike dark matter theories rooted in quantum fields or modified gravity, it offers no equations to falsify, no predictions beyond anything's possible. Even its most famous proponent, Elon Musk, admits it's more thought experiment than testable science, yet the idea persists not because it's provable, but because it reframes our deepest questions. If the universe's missing energy is a simulation's energy-saving mode, then the real mystery isn't what dark energy is, but who or what is conserving the power. Of course, Occam's razor favors simpler explanations. Dark energy could still be an undiscovered quantum field or a quirk of gravity, but the simulation hypothesis, for all its whimsy, serves a vital purpose. It reminds us that reality's puzzles might not fit the frameworks we've built to solve them. Sometimes progress begins not with answers, but with questions so outrageous, they force us to rethink everything we thought we knew, and in a cosmos where 95% of everything is missing, maybe outrageous is exactly what we need. From ghostly actions to cosmic holograms, from black holes birthing dark energy to the unsettling possibility that reality itself might be coded, our journey through the universe's missing energy has been anything but ordinary. Each theory we've explored, no matter how outlandish, represents something profound: humanity's refusal to accept gaps in our understanding as permanent. Whether it's tweaking gravity, inventing new particles, or rewriting the rules of spacetime itself, every idea is a testament to our collective imagination and determination to make sense of the cosmos. Think about it: we've mapped the stars, unraveled the atom, and traced the universe back to its first trembling moments, yet 95% of everything still eludes us. That's not a failure, it's an invitation. Every unexplained observation, every mismatched equation, is a cosmic breadcrumb leading us towards something deeper. Maybe dark energy is vacuum fluctuations, maybe it's the echo of a universe before ours, or maybe, just maybe, the truth is stranger than anything we've dared to propose. What's remarkable isn't just the diversity of theories, it's how each one in its own way forces us to confront how much we don't know. The fact that we can entertain ideas as different as MOND and multiverses, holograms and hidden dimensions, shows just how wide the playing field really is. And that's the beauty of science. It's not about certainty but curiosity. Every dead end teaches us something. Every wild idea, even the ones that don't pan out, stretches the boundaries of what's possible. So where does that leave us? Not with answers, but with something better: questions worth chasing. The universe isn't done surprising us, and that's what makes this search so exhilarating. Whether you're drawn to the elegance of supersymmetry, the audacity of emergent spacetime, or the sheer weirdness of simulation theory, there's a corner of this mystery with your name on it. Stay curious, dive deeper, debate, question, and wonder, because the greatest discoveries don't start with knowing, but with daring to ask. Now over to you: which of these theories sparks your imagination? The universe's greatest mysteries await your exploration. What's your favorite theory?